Oh, so who's gonna chair the session? All right, thanks for coming. So today I'm gonna give some introductory talk about isotropic systems because no one really knew about it, and I never actually gave a talk on isotropic system because nobody was interested. Yeah, some of my work were using this extensively. So I studied this when I was a PhD student, and this was one of the key tools which allows me to prove well-coordinated ordering of graphs of bounded rank list. So, but it's highly technical and not many people actually read the paper by Bouchet. His paper is not easily readable. It's a Bourbaki style paper. So, I mean, paper itself is not long. You have a sequence of papers, but the thing is, it is very abstract. Bourbaki style, so definition, and blah, blah, blah. So let me try to explain the definitions and key properties. But anyway, so the motivation for Bouchet to define, so this was 1887. Isotropic system was actually two things. One is the binary matroid, properties of binary matroid, and then the other is the properties of the Eulerian circuits in a four regular graph. But I'm gonna show the connection way later. So I will just show you the abstract definitions and then why it could be interesting. And my motivation is actually vertex-minors. Of graphs. So, all right. So let me start with the simple vector space. The simplest possible vector space consisting of only 4 elements. It's a vector space of dimension 2 over the binary field. So you can imagine that alpha is like 1, 0, beta is like 1, 1, no, 0, 1, and gamma is like 1, 1. Then alpha plus beta is gamma, and right. So alpha plus beta plus gamma is 0, and if you add the same thing, these are zeros. Now on this space, I'm gonna define an inner product. So for x and y in K, we're gonna define the inner product to be, bilinear form to be 1 or 0. If, the outcome is either 0 or 1 because it's binary field. So the value here is over the binary field. So we say it's 1 if x is different from y and both are non-zero. And you may want to check whether this is really a bilinear form. So whether this really is a inner product satisfying all the linearities. And indeed, it is the case. And you can, for instance, if you write this matrix form, then you can have a like y and x transpose, something like this. Okay, so all right, so that's my inner product or bilinear form on K. Yeah, it's too high. All right. Now we are ready to define isotropic system. And then we can finish the talk, maybe. So definitions. S is an isotropic system if V is a finite set and L is a subspace of K to the V such that so the two properties are. Oh, by the way, I didn't define the inner product for K to the V, but let me say, yeah. So for x, y in K to the V, we define the inner product by linear form between x and y is just the sum of the coordinate y's inner product. Okay. Then we say that L is a subspace satisfying two properties. The first property is that for any two vectors, the inner product is 0. Okay, so which is called, this property is called the totally isotropic. And the second property is the dimension of L is equal to the number of elements in the finite set. Then we say that S is an isotropic system. So it's just a pair of finite set and a totally isotropic subspace of K to the V with a certain dimension. And so here's some observations. So why is this dimension interesting? Because if L is a totally isotropic subspace of K to the V, then this subspace is the set of vectors which is orthogonal to all vectors in L, and which contains L, right? Because any pair is orthogonal. So L, this conjugate, the L per, yeah, this contains all L. So and we know the dimension of L. So this is time to remind yourself the one key theorem in linear algebra. The dimension of L plus dimension of L per is equal to the dimension of whole space. This is because this inner product is non-degenerate, so you can still use that, even though this is not a standard inner product. And this is twice V, because K already has a dimension 2. So the dimension of K to the V is twice V. And because L is a subspace of L per, so this is twice, at least twice dimension of L. So this means the dimension of L is less than or equal to V. Whenever you have a totally isotropic subspace, the dimension is at most the cardinality of L. So which means that this is maximum possible dimension of any totally isotropic subspace. And that gives a lot of combinatorial properties. Okay. If you have any questions, please feel free to stop me. I'll be happy to try to answer any questions if you have. Yeah.
K is not a field, but it is a ring.
K.
K is not a field.
Right. K is not a field. It's just a vector space over the binary field. Right. So K is this 4-element set. Right? 0, alpha, beta, gamma.
So why is K to the
Oh, so dimension of this?
So this K to the V is not a finite set, or is exactly the same?
Yeah, K to the V is a set of all functions from V to K. So for each element of V, you assign one element in K, but this is you consider this as a vector space over the binary field. So you can add two vectors. If I have A, B in K, then I can define A plus B as a function so that the V's coordinate is AB plus BV. But K itself has dimension 2, so the total dimension is twice V. So let me give you the example. So far, this is very abstract and it's not easy to see what's going on. So the key example to consider is the graph. So if I have a graph, let's say, let me do a simple example, okay? So this is path of length 4. Maybe this is better. House, right? So this is my graph. I want to construct an isotropic system associated with this graph. So what I do is think of the adjacency matrix. Right. So 1, 2, 3, 4, 5. All right. 1, 2, 1, 3, and 2, 4, and 4, 5, and 3, 5. Yes. Oh, 2, 3. Yes. That's it. And then with all the zeros. Oh, something's weird. Yeah. Right. I'm missing a row. Yes, that's right. 1, 0, and 1, 1. Yes. Yep. Now, what we do is I'm gonna replace diagonals by let's say I can choose anything. Let's say I choose diagonal to be alpha, and off-diagonal entries to be 0 or beta. And same way here. Maybe, let me. Yeah. Something wrong? Okay. So this is some matrix consisting of entries from K. And now I take L to be the span of the row vectors. All right. Now I claim that this is totally isotropic. Why? Let's compare two rows, right? So let's look at the first row and second row. What is the inner product between them? It's sum of the coordinate-wise inner product. Now, between beta or between 0, beta, 0, 0, all these values will be 0. Right? Inner product will be 0 if one of them is 0. Will be 0 if they are equal. So the only place they may have non-zero values when you have a diagonal entries. Because alpha, beta are different. So in this case, this coordinate contribute 1, but same 1 will be contributed by that because the matrix is symmetric. So the key property of the graph is that the adjacency matrix is symmetric. So 1 plus 1 is 0. Right? If I look at the other rows, other pairs, let's say first row with last row. Okay? Now, vertex 1 and vertex 5 are not adjacent. So if you look at the diagonal entries, corresponding value here is 0 and 0. For all other columns, it's either 0 or beta, so the inner product between them is 0, so they contribute nothing. So the only contribution to the inner product is coming from these diagonal entries, but in this case it's 0 and 0. So either it's 1 plus 1 or 0 plus 0, depending on the adjacencies. So that means for any pair of these rows, the inner product is 0. So the vector space spanned by these rows, the inner product will be 0. So that's why it's totally isotropic. Now, what about the dimensions? So why are they linearly independent? Well, when you try to add some linear combination of them, it's a binary vector space, so there's no coefficients, right? You just choose some subset and add them together. Then, let's say I chose, for example, I chose first 3 rows. Then these columns could be 0 or beta, right? So there are corresponding column indices, and these columns are outside of those corresponding column indices. So people outside this area, when you add them together, you may have a value 0 or beta, so it could be 0. But people inside these columns, they can never be 0 because you have at least one alpha. So if you have an even number of betas, then you have alpha. If you have an odd number of beta, you have a gamma. Because alpha plus beta is gamma. So you never have a linear combination, non-trivial linear combination whose sum is 0. Is it clear? So that's why this span of the row vectors of this adjacency matrix, this weird adjacency matrix, will have dimension equal to the number of vertices. So this is the key example, and we will see that. So this kind of isotropic system, for this isotropic system, we say that this is a fundamental graph of this isotropic system. Okay?
Do all isotropic systems have fundamental graphs?
Yeah, well, we'll get to that. Yeah. All right. So that's the key example. All right. Now, once we have this in mind, now we can define minors. Right, so how do we define a minor of isotropic system? And there are 3 kinds of minors instead of 2 kinds of minors. In a matroid, you have either deletion or contractions. But here, you will have 3 kinds of reductions. So I'm going to define, let's say it this way, V alpha. So V is some elements of finite set V, and alpha is non-zero elements from K. So what is this? So I'm gonna select all the vectors in L with AV is orthogonal to alpha. So I mean, this is same as saying that, in other words, this AV, the V coordinate is either 0 or alpha, right? So I'm selecting all the vectors whose V's coordinate is 0 or alpha and ignore the V's coordinate. So take projections. So I need the projection notation, some notation for projection. Let me write this way. Oh, not alpha, it's V. So this is projection. So this is a vector in k to the v minus v. Okay. Now here's the observation. 1. This is also totally isotropic subspace. Why? Yeah. So you ignored one coordinate, right? But between these two coordinates, between the ignored at the ignored coordinate, the inner product, the contribution was 0. So in the remaining coordinate, the contribution will be 0. Right? Between 0 and alpha, the inner product was 0. So if you ignore that, in the remaining vectors, you still have a inner product 0. So this is total isotropic subspace of k to the v minus v. And second observation is dimension of, so this is exactly what we wanted. So why? So the upper bound is easy because in totally isotropic subspaces, you always have upper bound, right? Because of that, whenever you have a totally isotropic subspaces, dimension is at most half of the dimension of the whole space. So that's the upper bound. What about the lower bound? One way to see the lower bound is, let's try to pick a basis. Let's say A1, A2, AN of L. All right. Now, when I pick a basis, I'm going to choose the basis so that the number of vectors in the basis with the non-zero values on the coordinate for v is minimized. Right? Choose so that number of I with AIV non-zero is minimum. Right? So you have two vectors in the basis whose v's coordinate value is the same, then I can replace one by their sum. Right? Elementary row operations. So if I have two vectors, right? If I have two vectors which is then I can add them together so that this becomes 0. So I try to apply elementary row operations and then until I have a minimum number of them. Then I have let me write it as a matrix form. So I have a coordinate for v and the all others. So what can happen? Maybe there are two cases. Maybe almost all are 0 except one coordinate is non-zero. That's one case. Or maybe almost all are 0 except two coordinates are non-zero. And these two are distinct. Why? Because, and you cannot have a 3 coordinate non-zero. Because if 3 coordinates are non-zero and distinct, then alpha, beta, gamma, then their sum is 0, so you can cancel 1, right? By adding two rows to last row. So this case never happens if I chose minimum. So either you have this situation where only one coordinate is non-zero, I mean one basis has non-zero value at 3, or two basis vectors has non-zero values at 3. Now, if this is the case, then by restriction, I have lower bound easily, because all other rows span they are all in this space. So then they are linearly independent, so they form bases. What about in this case? Well, if one of them is alpha, right? If one of them is alpha, then I am also happy, right? Because this combination will give me something. But am I doing all right? Maybe I'm cheating. Yeah, maybe you're wondering. Like, let's say this is alpha, this is beta. Now, I was hoping that they are linearly independent. But are they really linearly independent? If not, so there's a linear combination which makes these coordinates to be 0. But potentially that coordinate will make this could be still alpha. If it's right, if this is 0, then it's impossible because they were linearly independent, right? So this has to be alpha, right? So when I add some rows together, this will be alpha. So then what I get is 0, 0, 0, 0, 0, alpha. This vector exists inside L. But then it's contradiction to the totally isotropic property, right? So this vector is not orthogonal to that vector. Right, because the inner product between these two is 1. Alpha is different from beta. All right, so because of that, they are linearly independent. If you don't have alpha, then I can add one row to the other to make alpha. Right? If this is beta and gamma, then I can add a row of gamma to a row of beta to make an alpha. So they are linearly independent, which means that the dimension of this is at least number of points minus 1. Okay, so they are equal. All right, so that is a reduction. So that's how we define the minor. So what's called the elementary minor. So SV alpha or SV beta or SV gamma are called elementary minors. So you're doing one reduction. So this is like, this 3 operation is like, for matroid is like deletion or contractions. But now we have one more operations. So alpha reduction, beta reduction, gamma reductions. Okay, 3 possible reductions. Now what is a minor? S is a minor, S prime is a minor of S if S prime is equal to S V1 alpha 1, V2 alpha 2, Vk alpha k for some k. So if you can obtain one from the other by sequence of elementary minors, then we call it a minor. Oh yeah. So alpha I, yeah. So alpha i's are like one of these non-zero values in K. Right. So we have seen a definition of isotropic systems and minors.
Oh, do this twice, you don't get G minus 2 with upper bound. If you do this twice, it makes, say, V1 alpha 1, V2 alpha 2.
Right. Then if I do one once, I decrease dimension by 1, right? If I do one more, then I also decrease by 1. Because this is already isotropic system. Now, if I do one more, by this observation, will decrease the dimension inductively.
But the subspace of B minus B. Or,
Right.
right. And so the whole.
When you
Do it twice, then you decrease.
when you do this operation twice, then this is a subspace of K to the V minus V1 and V2, and the dimension of this is V minus 2. I mean twice V minus 2. Dimension of that. So this will give a totally isotropic subspace of that. So the upper bound is half of dimension of that is half of that. Yeah. Right. Any questions so far? Is everything okay? Yes. Okay, which order should I present? Now, so there's the graph example. That's, let me name it. So we say, so in that example, we have two vectors. One is alpha, 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 right? And the other is beta, 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 beta. So we use alpha for diagonals, use beta for non-diagonal edges. But actually, there are many more choices. Like for each column, I can decide what entry, what non-zero value I'm going to use for diagonals, and what non-zero value I'm going to use for off-diagonal edges. Right? So we say A, B are supplementary vectors. So both are in KV if AV, BV, when you take the inner product, then it's 1 for all V. So if I take A to be alpha everywhere and B to be beta everywhere, then they are supplementary. Now, for two supplementary vectors, A and B, right? We have this G, A, B, right? If you have a triple of a graph and two supplementary vectors, then I can construct the isotropic system where the coordinate and the diagonal entries are using A values, okay? And off-diagonal entries are using B values. And everything works out. So this is called the graphic presentation. Right? So you have many freedoms. Instead of choosing all alpha and all beta vectors, I can choose any pair of supplementary vectors, and that will give me another isotropic systems. Now, as one of you asked already, it'd be interesting to know whether there's a backward direction, right? Whenever I have an isotropic system, can I get a graph with the supplementary pairs of vectors? Any questions? And all of these are in the paper by Bouchet, so, but not just one paper, many papers, sequence of papers. But also in my PhD thesis, it's in one chapter. Yeah, so we put BV1 if the vertex corresponding to this is adjacent to the vertex corresponding, right? This row is adjacent to this column. Otherwise, 0. And then when you look at the two distinct rows, their inner product will be 0. So the span of these rows will be the space L. And L will be totally isotropic by the same reason as the other example. All right. Now, Bouchet defined the following. So X, we say X is an Eulerian vector. Of an isotropic system S if X is in KB. So X is an Eulerian vector if when you restrict X to, so X, first of all, XV is non-zero for all V. And I need some notations, but let me use a notation like this. So this is like induced vector. So this is a vector. So X, I don't know whether you like it or not. This is a vector where it's 0 if V is not in P. So P is a subset. P is a subset of V. It's 0. So outside I'm gonna ignore, make it 0. And inside I keep it. Okay. So if I restrict X to P, and then if it's in L, then then P is empty. So that's the definition of the Eulerian vector for an isotropic system, which is strange. So it's kind of vector. It's a completely non-zero vector. So that, and then if you have any such vector, then I can think of the n-dimensional vector space, subspace, just by taking restrictions, right? So ignoring some coordinate, making 0. So then I have a n-dimensional vector space. And this doesn't intersect my vector space L except at 0 vector. Then we say it's an Eulerian vector. So why is this related to our graphic representation? The thing is, when you have let's go back to this example. If you construct an isotropic system from graph, then here the diagonals form an Eulerian vector. The diagonals are alpha, 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 alpha. And in my isotropic system, there is no vector solely consisting of 0 and alpha, except 0 vector. Right? So if you have alpha, 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 and make somebody by 0, you can never have that in your span of these rows, because no matter how you try to span some vector, you're going to have either gamma or, oh, maybe I'm wrong. Am I doing all right? Maybe something wrong. Maybe beta, beta, beta. Yeah. You can never make a beta. That's the, yeah. So beta is a Eulerian vector. Okay, I should change my wording. Right. Any linear combination will never create a vector which consists of only 0 or beta, because you're gonna have alpha or gamma in some row, in some column, in some coordinate. Yeah. Right. Any linear combination will either have alpha or gamma in some column, so that's why you can never create beta. So here, beta, beta, beta is Eulerian.
Oh, it doesn't have to be in L.
Oh, it's not in L.
Oh, okay.
It cannot be in L actually. We don't want to have any intersection with L. It's something outside. So we have L, right? We have L. We want to pick some vector so that all its shadows will never intersect my L except the 0 vector. It's kind of orthogonal thing. Okay, that's the Eulerian vector. So in this case, a vector consisting only of beta is an Eulerian. Potentially, you may spend gamma, 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 gamma. Potentially. I mean, the Eulerian vector is not unique, but you may, depending on the edges, you may have all beta or all gamma, right?
I guess you can't have both. You can't, like one or the other might be over there. You can't have alpha, alpha, for the and gamma, gamma, gamma. And you can construct beta, beta, beta.
Well, no, actually not, no. All right, so here's the theorem by Bouchet, which tells you that you can always find an Eulerian vector in an isotropic system. Not only that, you can always find an Eulerian vector which is supplementary to my given vector. So let C be a vector such that CV is non-zero for all V. Then S has an Eulerian vector supplementary to C. So for any C, I can always find an Eulerian vector which is supplementary to my choice. So why? And the proof is by induction. Induction on number of points in V. Oh yeah, by the way, if you forgot the definition of supplementary, supplementary means that coordinate-wise inner product 1. Right. What is S? Isotropic system, yeah. Then an isotropic system, either beta or gamma. Right. Yeah.
So you can take actually C to be a Eulerian vector. So
right.
All beta vector here.
And then you give another one.
And what you get is all gamma vector because if you got an alpha of any coordinate to that.
That's right. You can always move from one Eulerian vector to another Eulerian vector. Keep finding new one.
Well, maybe get new one, or do you just go back and forth?
You can always go. Yeah. So there's a connection. All right. So the proof is simply induction. So if you have only one element, then it's trivial, because in this case, isotropic system only has dimension 1. So it's span of alpha or beta or gamma. So if my C is something, like C could be alpha, and my L is beta, then I'm gonna choose the remaining one, gamma, for instance. So that's trivial. So now we assumed that the V has more than one element. So suppose not. So that means there's no Eulerian vector supplementary to C. And let's assume by symmetry that let's assume that C of V is gamma. So pick V in V, and so I choose one coordinate, and let's assume by symmetry that that coordinate value for C is gamma. Now let's look at the S restricted, take an elementary minor. With gamma. Take an elementary minor, reduced by gamma. Now, this is an isotropic system, so we can apply induction. So there is a Eulerian vector. Right. Oh. Should I keep it? Maybe. Too late. But I can keep here, right? Okay, maybe keep. All right. So I have a Eulerian vector, and then if I attach A with alpha, then this is not an Eulerian vector by assumption. So this notation means I have A, but I attach alpha. Now it's a vector in K to the V. Okay. And this is not Eulerian. So what does that mean? That means I can restrict to some subset, and then it's going to be in L. For some x, which is non-empty. Oh yeah, A is supplementary to P V minus V C, the projection of C with respect to the V minus V. Yeah, right. So alpha is different from gamma, so this is supplementary to C. So therefore, it is not Eulerian. That means there's one way to restrict it, so that if I ignore some coordinate to be 0, then it becomes a vector in L. And similarly, A plus beta is in L if we restrict to some subset Y. And the thing is, if X doesn't contain V, then that's contradiction, because if X does not contain V, that means A already can be restricted to somebody in the minor. But A was an Eulerian vector, so no matter how I try to restrict, it's not going to be in my space here, right? L, V, gamma. But if that one's A plus 0 was already in L, no, that's not what I mean. No, this thing was in L, right? But if X doesn't contain V, then that one looks like 0 and something. But this is going to be in LV gamma. There's a contradiction to the fact that A was an Eulerian vector for this guy. So that means X contains V, and similarly Y contains V. Now, these two vectors are in L, and they both contain V, so their sum is also in L. Because it's a vector space, their sum is also in L. But what's going to be the sum? Alpha plus beta will become gamma. And so if you take a sum, then what you end up is something like, here you have a gamma, and here you're gonna have a restricted to the symmetric difference of X and Y. So this vector is in L. Now, if I look at the LV gamma, this will, so if I ignore gamma, then this vector is in LV gamma. So that means A restricted to X delta Y is in LV gamma. Now, A was Eulerian, so that means X is equal to Y. Because X delta Y is empty. So X is equal to Y. What does that mean? That means 0, gamma. That vector is in L. This is 0, right? 0 gamma is in L. That's weird because, right? Then what happens? We said that A plus alpha is in L. But this is not orthogonal to that. Right? This X contains V. So the inner product between these two is 1. With 0 to A is 0, but gamma to alpha is 1. So that's a contradiction. L was totally isotropic. So all this linear algebra proof gives you something. All right. So that's it's not immediate, but let me. Oh, maybe I should speed up because it's related to number of equivalence classes of graphs up to local complementations. But all right, and now maybe this theorem I'm gonna just state the theorem. So let's say A is Eulerian vector of isotropic system. Then, so if I have an Eulerian vector, then maybe I should have chosen, yeah, my definition of graph. Okay. Anyway, too late. For all V, there is a unique vector BV in L such that BV V is non-zero and BVW is supplementary. So BVW is orthogonal to, I mean, no, not supplementary. It's so this means that BVW is in 0 or AW. And the proof is again some linear algebra type of proof, you can imagine. So why is this interesting? And furthermore, yeah. When you collect this, this is a basis of L. So this is called the fundamental basis. So with respect to Eulerian vector A. So if I choose an Eulerian vector, I have a unique choice of vectors. So that for all, so for each point, the coordinate values not on that coordinate will be either the 0 or same as Eulerian vector, but that coordinate doesn't have a non-zero value. But since it's Eulerian, this already implies that BV is K minus 0 and AV. So you're gonna have something other than the Eulerian.
Why does that imply that?
The reason is A was Eulerian and B is in L. so far, if you look at these situations, all the coordinates are same as Eulerian vector. But definition of Eulerian vector doesn't allow such a vector to be in L. So the only way this is Eulerian is you have to avoid being AV or 0. So you have to be some value other than, like if AV is alpha, then you have to be beta or gamma, so that A become Eulerian. Right? So once you have this, then you can define fundamental graph. With respect to A. Like it's a graph G on V where X is adjacent to Y if and only if BX, Y is non-zero. Yeah, but you can see that Bx and By, the inner product between them is 0 because it's totally isotropic. So that means Bxy plus Bxy. Yeah. So I mean, this means that So right, this means that Bxy and Bxx plus Byx, By. Am I doing it right? Something's no, By. B, X. Byy, This is 0. So if this is 0, this is 0. This is non-zero, this is non-zero. And that is same as this. So this gives you an undirected graph. So that's the fundamental graph of the isotropic system. And maybe I can describe why this would be interesting. And this is unique. If you're given an Eulerian vector, you have a unique fundamental graph. Now, then you may wonder what happens. Like, what are they? Oops. Why is this interesting? Because you have minors and fundamental graphs. Maybe I will finish by explaining connections. If A is an Eulerian vector, and if we apply that theorem, then I can get another Eulerian vector. Like, I want to switch the V coordinate. I have another Eulerian vector. And this is related to, so if I go to fundamental graph, what I get is graph obtained by local complementations. What I mean is, like, so let me give you examples and, right? So I had a house, right? Now, what is local complementation at this vertex V? That is to replace its neighborhood by its complement. So if two vertices are adjacent, it becomes non-adjacent. Now, if I apply local complementation at this vertex, what does that mean? That means now I had an adjacency matrix, right? Now let's say this was my V. I look at the neighbors. Right? If these are neighbors are maybe something like beta, and 0, 0, beta, 0, 0. In simplistic example, this was my graph. And how do I obtain a graph obtained by doing local complementation at V? I add this row to other rows. Do the elementary row operations. Then beta becomes alpha plus beta, so gamma, gamma. And beta plus alpha is gamma, gamma, and beta, beta. And everything else is same. Now, this spans same vector space. But now the Eulerian vector that I'm using is gamma, beta, beta, and beta, beta. And this is the Eulerian vector I'm using. Initially, the Eulerian vector I'm using was beta, 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 beta. So this is what I mean by switching at V. By switching at this coordinate, I have a new representation, but the corresponding graph is this. So they make a same graph. I mean, same isotropic system. So these two graphs look different. They are related by local complementations, but they make the same isotropic system. So vertex-minors. So then you can do all this, like what is the S3 alpha in this case? Well, you can just, the easiest one is SV beta. That is same as ignoring this row and column. So that is the same as deleting V in this case. What about SV gamma? Well, you look at this. Then you can ignore this. So this corresponds to G local compensation gamma, no, V, and delete V. What about beta? How do I make a beta? No, that's where you do pivot operations. So if I have a, maybe, but I'm running out of time. So if you want to see, so just let's say I have an alpha. So let's say I have two vertices VW, which are adjacent. What I do is I look at their outside of this matrix. I look at their common neighbors. So these are common neighbors. These are neighbors of left, neighbors of right. LR. Okay. Now I look at the. So this is my vertex V. Then neighbor. So left hand side is neighbors. So this is beta and beta 0. Beta, beta, 0. So what this means is the row of complete vector. And by symmetry, this is beta, beta, 0, beta, beta, 0. Now, what I do is try to add this row over here. So over here. To make these beta to be gamma. Okay? And then try to add, no, maybe I'm wrong. Yeah, maybe over here. Yeah. So this part will be flipped. So beta plus beta becomes 0. Gamma plus that one, and then add this row over here. So what you end up is, what's going to happen? So this beta becomes 0. Okay? And this is common neighbor. So what you end up is, I'm adding this over here and adding that over here. So it's becoming alpha. Maybe I'm cheating. It's not symmetric. Maybe it's one of these two. Oh. Okay, let's do it. The initial way was correct. So let me add this over here. Then this becomes 0. All right? And they are flipped. And then add this over. Oh, maybe okay, let's see.
You want to do
Yeah, I want to do pivot, and
like local complementation with V, then W, then V again, right?
yeah, that's the same thing.
W, I guess, is the second row.
Yeah, this is second row, second row and second column.
So
Oh,
maybe first at the first row, right? And then
so that's first row to oh, I see. So
it's a guess.
yeah, I forgot these details, but what you end up is you have a matrix where these become alpha. This row, this column become alpha or something else, and then the reduction corresponds to the this graph. So in summary, so this means that any graph which you can obtain by a sequence of local complementation pivot can be written as a fundamental graph of isotropic system, which is a minor of your initial isotropic system. And then here it's a lot easier to understand vertex-minors because you have fixed vector space and you just restrict to some coordinate alpha, beta, gamma. And then you can look at the vertex-minors. And if you want to look at the pivot minors, you only need to use alpha and just 2 values instead of 3 values. If you use only 2 reduction, then you get a pivot minors. So that's the messages, and there's connectivity notions, and yeah, lots of. So one thing I use this concept is that I have a C code to generate like all graphs, which is locally, which you can obtain by doing local complementations. And one way to do it is starting from a graph G, you construct an isotropic system, and then there are 3 to the n possible complete vectors, 3 to the n possible Eulerian vectors, and check whether or not they are Eulerian. If they are Eulerian, then you can construct the fundamental graph. So given an isotropic system, you can construct a fundamental graph. So which can generate all graphs locally given to that. And that's actually the key idea where you use, you can use it to test vertex-minors of graph. So we use isotropic systems. But anyway, I spent too much time. Thanks for listening. Thank you.
Any questions?
Is there any property whose fundamental graph is PU?
So that property is not precludes on the taking local complementation, so you cannot say much about it from isotropic systems. So Bouchet used this to prove the obstructions for circle graphs. So circle graphs are characterized by like forbidden vertex-minors, but you can look at the isotropic system and do something. Anyway, this is, if you like a matrix, there are lots of interesting connections.
We have a comment from Unjong. Awesome intro, thanks.
Okay, thank you.
So when you apply this switch at a point V,
Yeah.
Let's suppose that you did this just so. Suppose you only calculate the Eulerian vector, and then can you is it possible to determine the new Eulerian vector you will get after applying the switch, sort of without looking at the fundamental graph?
You need to look at it. So
But determined, I guess, because the fundamental graph is determined. So I guess it has to be, right?
so the thing is, so this So the name Eulerian vector comes from the Eulerian circuit in a four regular graph. So what that means is you have, let's say you have a four regular graph. So Bouchet's motivation was to look at the set of all circuits which is Eulerian. So I might be screwed. No, not yet. Maybe. Okay, this is not an Eulerian. This is not a good example. Oh yeah, I mean, my initial drawing was Eulerian circuit, right? So right? Now, what you do is, how do you get an isotropic system? At each vertex, at each intersection, you have three possible transitions. You have these transitions, or you have that transitions, or you have that transitions, right? At each crossings. So you just pick alpha, beta, gamma, and you can see that you just pick, oh, this is alpha, beta, gamma, and that's an Eulerian system. Eulerian circuit. So Eulerian circuit corresponds to the Eulerian vector. So the thing is, if you flip here, so let's say I want to flip here. How do I know that this is a new Eulerian circuit? Well, if I know the global structure, okay, this is like this, okay, maybe I know that this is the Eulerian circuit or that's the Eulerian circuit. So one of two will give me a new Eulerian circuit. So that corresponds to the switching.
Is it always true that exactly one switch will give you a new Eulerian circuit?
Well, the thing is, yeah, if you look at this picture,
oh yeah,
yeah, I mean you don't want to have this. But one choice will make a bad choice.
One choice is bad.
Yeah. So, and there was an old theorem that if you have a four regular graph and you at each crossing you forbid one possible types, then there exists the Eulerian circuit avoiding it. That's the combinatorial version of this.
Right. So whenever you have an Eulerian vector now, is it the same thing where you can? There's always one choice to switch any coordinate to get a new Eulerian vector.
Yeah. So this is the thing. Right. So this combinatorial theorem about the existence of a Eulerian circuit forbidding one crossing is exactly this statement. So all these connections make it so difficult to read the papers because you may have to know all this background in order to see why this is interesting.
Right. But sometimes you do the switch, because I was thinking sometimes you do the switch and the fundamental graph doesn't change, right? Like if the
yeah, right. Yeah, that happens.
But you still have the same thing when you look at the Eulerian vectors, where they still switch.
Yeah. So because of these connections, you could say something about like vertex-minors from the perspective of four regular graphs. So these four regular graphs correspond to the circle graphs, and the vertex-minors of circle graphs correspond to this directed graph. Anyway.
Another question from Unja. Does perfect matching have some connection with isotropic systems?
Perfect matchings, I don't think so. Yeah, I don't know. I'm pointing to the camera. Huh?
You're outside the frame.
Oh, I see. Right. I'm not aware of connections to perfect matchings.
Some kind of map theoretic application?
Yeah, right. This looks like, there may be, but I don't know. The people define some polynomials based on this. So, and some people define isotropic polynomial or interlaced polynomial. So Bolovas and two other people define interlaced polynomial based on these three reductions: G delivery, local competency delivery, and it corresponds to, if you look at the isotropic system, then it's related to these three reductions.
And then there has to be the open-ended question: is there a connection with matroid?
Yeah, I mean, there's a connection to binary matroid. So from the binary matroid, you can construct the isotropic system. And yeah. So basically, that's the case when fundamental graph is bipartite. If the fundamental graph is bipartite, then what you get is isotropic system coming from a binary matroid.
Relate to the binary delta. It's just the same.
Oh, so delta matroid. Yeah, so delta matroid. So basically, this whole thing is also related to binary delta matroid. Right. Maybe we should stop and people. Otherwise, everybody will.
Okay, then thank you again.
Thank you.